Okay, welcome Woodstock students. Here is another discussion of motors and their characteristics, particularly just thinking about um, the rotational rate and voltage levels needed when the motor is operating with or without a load. We last took a look at this situation here of a motor that was driving a kind of a simple little conveyor belt system, and we talked about the no load situation where the velocity increased linearly with the input voltage, and how the slope of that basically dropped with modest and then heavy loads. So in this little video we're going to take a look at kind of a sample set of problems. Let's suppose that under the conditions of no load, a motor can spin at a rate of 2400 RPMs when connected to a 9-volt battery. And so we can ask a number of questions. What if we drop the voltage down to 1.5 volts? What would our anticipated spin rate be? Okay, that may seem pretty straightforward. What kind of battery would you need to get it to spin at 1000 RPM? And then finally, maybe the most kind of complex kind of situation, given this no load situation, what can we expect to happen if, I'm sorry, how much voltage would we need to get the spin rate under a certain load to be 1500 RPM? And what we are told is that the load reduces the maximum spin rate by 30%. So if you want to pause the video and try to address those questions, you could go ahead and do that. Okay, but I'm going to go right ahead and try to address these questions. So let's cover up a good portion of this. Okay, look at one piece at a time here. So these problems basically involve a lot of proportional thinking, since the relationship is linear. So we just need to be thinking about the ratio of voltages and how that impacts the resulting spin rate and so forth. So here's the ratio of voltages, right? 1.5 over 9 is 0.166 as a ratio. That turns out to be exactly 1/6. So 2400 times 0.166 would give us 400 RPM. That's the anticipated spin rate if we drop the voltage level down from a 9-volt battery down to a 1.5 volt battery. So exactly 1/6. Okay. Again, another kind of proportionality. Maybe what voltage do we need to get it to spin at exactly 1000 RPM? Well, what portion of the top spin rate is this? So it's 1000 over 2400. It's 41.6% of the maximum spin rate, or 0.4166. If we apply that to the 9-volt battery, we would need exactly 41.6% of the 9-volt battery, or a 3.75 volt battery. So I'm not sure you can get that at the store, but you might be able to kind of rig up something to get exactly that voltage. Okay, let's scooch down here a little bit and take a look at the final problem. Okay, we're going to now subject the motor to a load, and that load reduces the maximum spin rate by 30%. So first we'll have to correct for what the maximum spin rate would be at 9 volts, and then figure out the voltage necessary to get the loaded motor to spin at a 1500 RPM. So the first part is to get the new maximum spin rate. It's the old rate, 2400, less 30% of 2400. Of course, that is the same thing as just calculating 70% of 2400. Excuse me. And that calculation turns out to be 1680 RPM. So 1680 RPM is the new maximum spin rate at 9 volts. Okay? Now we apply our proportional thinking again. Okay, we want it to spin at 1500 volts, not 1680. So that's pretty close. Let's figure out what that percentage is. 1500 over 1680 times 9 volts is going to be 0.893 times 9 volts, or 8.40 volts. Again, that's not a voltage or battery voltage you can get at the store, but you can probably get pretty close to that by adding up 3-volt batteries and 1.5-volt batteries and such, and you could probably come up with some combination that would be pretty close to that. Or maybe just run it with a 9-volt battery and I don't know, add in some kind of resistor or something. We'll talk about that at another time, how we might drop a voltage down in some manner like that. Okay, that's all for now.